Hello, everyone. I am Hao King from Mercedes-Benz and University of Bonn. I would like to present our work at Cvpr 2026 Pqdt, a pseudo-query dual transformer for robust point cloud restoration. Real-world 3D point clouds suffer from multiple co-occurring degradations: incompleteness from occlusion and limited sensor coverage, noise and outliers from sensor inaccuracy, and geometric deformation from registration errors. As you can see on the right, these degradations rarely occur in isolation. A single scan can be incomplete, noisy, and deformed simultaneously. Existing methods typically address each problem individually, but they struggle when these corruptions are combined. Let me briefly categorize prior approaches. Bottleneck-based methods compress the input into a global latent code, which loses fine-grained geometry and is fragile under noise. Seed or query-based methods improve on this by producing point proxies from coarse features, but they still decode directly from corrupted input, making them sensitive to noise, outliers, and distorted geometry. Our key insight with Pqdt is to decouple the reconstruction from raw input quality by introducing noise-resistant pseudo-queries as intermediate representations. Here is the Pqdt architecture. We reformulate restoration as two cooperative stages. In Stage 1, observation-guided pseudo-query generation, we encode the source features QSRC through our geometric embedding encoder ME1, then decode spherical queries QSPH through our decoder MD1. A dynamic query selection module S1 filters the best pseudo-query candidates QPS. In Stage 2, prior guided refinement, we re-encode these pseudo-queries through ME2. Apply another DQS module S2 to select consolidated queries Q, and finally our decoder MD2 produces the output proxies H from the queries and refined features V. The attention maps on the right demonstrate our dual-stage design. Stage 1 captures broad structural patterns, while Stage 2 produces progressively localized surface-aligned attention. Importantly, this is a single unified model. No task-specific heads are needed. Let me highlight two key modules. On the left, our geometric embedding self-attention captures transformation-invariant spatial relationships. We compute sparse geometric embeddings Rij that encode both pairwise distances and triplet angles among k nearest neighbors, then incorporate them as additional keys k, r, and values vr, alongside the standard feature-based keys and values. This enables geometric awareness even under deformation. On the right, the dynamic query selection module adaptively filters redundant or noisy candidates. We compute standardized scores Zi through an MLP, perturb them with Gumbel noise scaled by beta, and apply hard top K selection. Beta is annealed from 1 to 0 during training, starting with exploration and converging to deterministic selection. A straight-through estimator enables gradient flow through the discrete selection. We evaluate on 4 benchmarks: ShapeNet 55 and 34 for standard point cloud completion across multiple difficulty levels. And we introduce 3 new challenging benchmarks. ShapeNet Deform applies Gabor noise as geometric deformation combined with incompleteness. ShapeNet Car OCC simulates realistic LiDAR occlusion with sensor noise. And PFS, patchified freeform surfaces, from real automotive body-in-white components, where local deformation restoration is required. As shown in the table, Pqdt achieves state-of-the-art across all benchmarks using a single unified model with no task-specific tuning. On ShapeNet 55, we reduce chamfer distance by 10.5% over the previous best. On the unseen categories of ShapeNet 34, we improve CD by nearly 14%, demonstrating strong generalization. On our new deformation and occlusion benchmarks, Pqdt consistently outperforms all baselines in both CD and F1. Most notably, on the PFS industrial dataset, We achieve a 77% reduction in CD and 27% improvement in F1, showing that our dual-stage approach is particularly effective for challenging real-world geometry restoration. The visual comparisons confirm our quantitative findings. On ShapeNet Deform, you can see that competing methods produce noisy or incomplete surfaces, while Pqdt recovers clean, consistent geometry. On ShapeNet Car OCC, despite severe occlusion and noise, our method reconstructs plausible car shapes. And on the industrial PFS dataset at the bottom, Pqdt accurately restores local surface geometry. The other methods either hallucinate structure or fail to remove deformation artifacts. To summarize, Pqdt provides a unified point-only backbone for robust 3D restoration, handling completion, denoising, and deformation correction simultaneously. Our Pseudo-Query Dual Transformer design with adaptive query selection achieves state-of-the-art across all benchmarks, including 3 newly introduced datasets. Code and data are publicly available. Thank you for your attention.